Professor Evan Kirby, who shortly will be at Caltech. And he's an observer by trade, but he actually knows just about everything. And so you heard the lectures by Yong Chen last week, and also Joel to open the workshop on chemical evolution and theoretical issues in chemical evolution. Well, here's the real deal.
That is a lot to live up to, but hopefully this won't be at too low a level for you theorist-oriented, theory-minded people. I'll try to be slow. If I'm going too fast or anything, please let me know. So here's sort of the schedule that I have in mind, and we can change the schedule if it works for you differently. But today, a little bit earlier today, I'm going to be talking about the sources of nucleosynthesis and their timescales. So to understand a chemical evolution model and to understand how the elements evolve in a galaxy, you need to know where the elements are coming from, what those things are making, and how long they take to make them and to spew them out into the galaxy around themselves. This afternoon, I'm going to be doing a workshop with Carla. We're going to have, maybe it's still 5:30, I'm not sure, but we have 2.5, 3 hours or so to make our own chemical evolution model. So Carla is going to walk you through how to make R process yield. So you're going to be making the R process in your computers, and I think she's going to experiment with whether or not that R process comes from supernova or neutron star mergers. And then you can take those yields and the different timescales for those two processes, put them in the chemical evolution model that you've just made, and see whether or not you can reproduce the observed pattern of europium in one of the dwarf galaxies that I'll be talking about in the workshop, based on whether or not our process comes from supernova or neutron star mergers. Here's a hint, it's going to be ambiguous. On Tuesday, tomorrow, I'll be talking about analytic models of chemical evolution. So today you'll be making a numerical model of chemical evolution, but tomorrow we're going to analytically solve the equations of chemical evolution, and we're going to be approximating out the wazoo. So we're going to be assuming instantaneous mixing, instantaneous recycling, all these things that you really shouldn't do. But we're going to do for convenience because then we can get analytical solutions to the equations of galactic chemical evolution. And just a warning, there's going to be lots and lots of equations tomorrow, but you people like theory, so you don't care. And on Wednesday, we're going to be talking about actual measurements of elements in the galaxy, in the Milky Way galaxy, and beyond the Milky Way galaxy. So how do you measure the chemical elements of the periodic table, and how can we use those measurements to interpret where these elements are coming from and apply the equations of galactic chemical evolution to actual measurements of things like the metallicity distribution and plots of the alpha-iron ratio versus iron. And so hopefully if you've ever been mystified by a plot where you see all these elements thrown at you like chromium and neodymium and samarium and europium, finally we can figure out what all those things mean in the context of where they come from in the galaxy and what sources in those galaxies are making them. So here are some hopefully useful links. This is my website, and I have a little folder in there where you can find all of the lectures for today, tomorrow, and Wednesday, and also some files that are going to be relevant for the workshop. And I've also put these on Gordon. Carla told me that she couldn't quite access them, and there might be some permission issues. I think I fixed that, but I've had some redundancy, so you can go to my website, or you can go to Gordon to download these things. And in particular, this file is going to be very important for later today. It's the walkthrough for the workshop. It's 4 pages long. We only have basically an hour and a half for my chemical evolution section of the workshop. And this walkthrough is 4 pages long, but I've tried to make it step by step. It's long not because there's a lot to do, but because I've walked through every little step because there's just not that much time to actually make this chemical evolution model. This chemical evolution model that we're going to be making is very basic. It does not at all require the computing power of Gordon. So you can just use your laptop. You could write in IDL, you could write in Fortran, you could write in BASIC if you wanted to. It's just going to be integrating some equations. Okay, so now I'm going to be talking about where the elements in galaxies come from. So the sources of nucleosynthesis, we're talking about supernova, AGB stars, all kinds of things. And then their time scale. So how long do they take to make these elements, and how long do they take to spit them out into the galaxy surrounding them, so we can actually measure what the alpha to iron ratio is as a function of metallicity. So I'm going to give you a quick orientation to the elements. I don't know how many times last week you saw the periodic table, but you're going to see it again. And then the nucleosynthesis sources. So the major ones that I'm going to be talking about are the 2 main types of supernova. We have core collapse type 2 supernova, and then the thermonuclear type 1a supernova from low mass stars. And finally, AGB stars are also going to be very important for certain elements of the periodic table. It's Speaking of that periodic table, there it is. You probably play a drinking game with how many times you've seen it this week. But the first two elements, hydrogen and helium, as you know, come from the Big Bang. Just a tiny bit of lithium also comes from the Big Bang. But the rest of the table is made in stars. So stars make every single thing else in the periodic table. And the lighter the element, the more abundant it is because it's kind of easier to make. And then as you get to higher and higher energies in these nucleosynthetic sources, as you've already heard about in this workshop, in this summer school, you get to heavier and heavier elements until finally you get to around the iron peak, especially nickel 56, which has the lowest binding energy per nucleon. You make tons and tons of it in these supernova. And then beyond the iron peak, we have all of these heavier elements that can only be made through neutron capture. So we're going to be talking a little bit about those neutron capture elements. And especially Carla is going to be talking about those neutron capture elements as they're made in the R process. So at the end of this lecture, I'm going to be talking about the difference between the S and the R processes very briefly. So here's a cheat sheet for nucleosynthesis. When you go back to that periodic table and you want to know where does this element come from, this little cheat sheet tells you exactly where those elements come from. And there's also a very important reference in the literature that I'm going to be bringing up later, Woosley and Weaver, 1995, which the last table in that paper is a much more sophisticated version of this cheat sheet. So if you're ever curious about where a particular element, and even where a particular isotope comes from in the universe, you can go to these cheat sheets and say, yep, that's where it comes from. It comes from this nucleosynthetic source, or more often than not, from these multiple nucleosynthetic sources. So type 2 supernova make the hydrostatically burned element. Type 2 supernova are high mass stars. That's how they start off their lives. And so what that means is they make all of the elements that you can make hydrostatically. So you start off with hydrogen, and then you turn the hydrogen into helium hydrostatically. And you can turn helium into carbon hydrostatically. And you can make CN&O all through helium burning, and then the sub-process of the CNO cycle and hydrogen burning can alter the relative abundances of CN&O. You can make the alpha elements because you can start off with carbon, and then you add a bunch of alpha particles, and you can smash them together until you get oxygen, neon, magnesium, silicon, sulfur, argon, and calcium. Those elements are called the alpha elements because you can sort of think of them as taking an oxygen nucleus, keep smashing on alpha particles until you get heavier and heavier elements. And then somewhere around there, it doesn't really work anymore when you get to calcium. Some people lump titanium in with the alpha elements, but it's definitely made through a different process than smashing alpha particles onto these nuclei. They make some iron peak because when they blow up explosively, they can reach nuclear statistical equilibrium. You can get all of these iron peak elements made, and when they blow up, they can spew all of that stuff out. So it's not just the stuff that they make explosively that they spew out in the explosion. They also spew out all the stuff that they made hydrostatically. So you can think of the supernova as an onion shell model with all of these hydrostatic layers on the outside and then the explosion on the inside. It's possible that these supernova also make some R process, and I'm going to leave that to Carla to explain. Type 1a supernova come from low mass stars, and so they don't have a lot of hydrostatically burned elements. They don't ever get hot enough, or I should say they never reach oxygen burning, for example. They never reach silicon burning. They don't ever even reach carbon burning. So the stuff that comes out is made in the explosion. So what mostly comes out is the stuff you get from nuclear statistical equilibrium, which is the iron peak. So basically scandium to zinc comes out of these type 1a supernova. So you have some of these iron peak elements coming from type 2 supernova, but mostly they come from type 1a supernova. And we'll see that that ratio of whether these iron peak elements come from type 2 versus type 1a supernova depends on the metallicity, or actually the look-back time, and we'll see why. And finally, AGB stars, which are sort of intermediate mass stars, make some of the lighter elements and also some of the heavier elements. So things lighter than the iron peak and things heavier than the iron peak. So they make helium, carbon, nitrogen, and also the S process elements. So neutron capture through the S process. So I'm going to compare this graph with the one that you're about to see next. This is the average binding energy per nucleon. I'm sure you've seen this before, versus the mass number of the nucleon that we're dealing with. So you can see that we start off with hydrogen way down here, and then lithium has the first peak, and then, sorry, not lithium, that's helium. So helium has the first peak, and then mass numbers 5 and 6 aren't very energetically favorable. Then we have a big bump at 7. And so you can see that elements are going to build up where we have these peaks, and then finally, there's going to be a big peak in the abundance distribution of these iron peak elements because they have the lowest binding energy per nucleon. So when we look at the actual abundance of the universe, or let's say the abundance of the sun, versus mass number, we can see where those peaks are. So where that iron peak is, we have a lot of stuff being built up there because nuclear statistical equilibrium causes everything to go towards iron and nickel. And then all these other little peaks are because the average binding energy per nucleon has a peak in that graph that we saw in the previous table. So for example, we don't get a lot of beryllium because there's just not a lot of average binding energy per nucleon for beryllium. And so now I told you the cheat sheet, so let's go into a little bit more detail about these nucleosynthetic sources. We have the major nucleosynthetic sources, which we already talked about, were the core collapse supernova, the type 1a supernova, and also these AGB stars. Now, the important thing for chemical evolution is how long these things take to make these elements and how long they take to spew them out into the galaxy. Because if it takes a very long time for that iron from these type 1a supernova to get into the galaxy, then there's going to be a long delay time for that iron. Once the stars are formed, it's going to take a very long time for that iron to actually get into the next generation of stars. So these core collapse supernova are basically just the lifetimes of massive stars, which is 4 to 25 million years. That's a very, very short amount of time. So basically, as soon as these stars are born, they die. And when they die, they put a lot of these alpha elements and a little bit of iron into the galaxy surrounding them. So this oxygen and all these alpha elements have a very short delay time. So if you see oxygen and alpha elements, it probably came from a high mass star that just died. So if you look at a plot of the oxygen to iron ratio versus iron, and you see oxygen there, that oxygen came from stars that just died. So the oxygen is coming from stars that died at the metallicity that you're observing it at. Now, these AGB stars have a longer time scale. They live with a lifetime of basically an intermediate mass star, which is 50 million years or greater. So they have a slightly longer delay time than these type 2 supernova, not that much longer, but this range extends basically to infinity because lots of stars are going to end up as AGB stars. The sun's going to end up as an AGB star. So it's going to take 8 billion years for that to happen. So these AGB stars tend to pollute a lot at early times, and then they still pollute later pollute some at later times. Then finally, these type 1a supernova take a very long time to go off. And so the lower limit for type 1a supernova is very uncertain. We're going to go into a little bit of detail about the delay time distribution for type 1a supernova, but they can last as long as the age of the universe. So these type 1a supernova have a built-in delay of probably about 100 million years, maybe a little bit less. But then they continue to go off for as long as the age of the universe. So as long as you have a significant amount of stars being formed, you're going to have type 1a supernova going off forever. So long after the oxygen from these type 2 supernovae ceases to be produced, you're going to have iron from the type 1a supernova being produced. And finally, there's a bunch of minor nucleosynthetic sources. Here's a few of them. We have winds from low mass stars. So low mass stars, even like the sun, are losing mass, and they can spew whatever's in their envelopes out into outer space. We have neutron star mergers, which are possibly a source of the R process. I think Carla's going to talk about that. We have cosmic ray spallation, where cosmic rays can strike a heavy nucleus and break it apart. This is a dominant way of producing lithium-6 in the universe. Okay, so here's a very undergraduate representation of the Hertzsprung-Russell diagram, and you can see that the massive stars are way up here, and there's the ones that make type 2 supernova, and you can see their lifetimes are very short. And this is exactly why the delay time for type 2 supernova is so much less than the delay time for type 1a supernova. It's really just the lifetime of the star. So the stars that make type 1a supernova are down here and up here. They have much longer lifetimes. You can see 10 to the 9, 10 to the 10 years. Whereas the stars that make type 2 supernova and all those alpha elements 10 to the 8, 10 to the 7 years. So that's why the elements like oxygen and the alpha elements have short delay times, and the elements like iron have longer delay times. So here's that onion skin model of a core collapse type 2 supernova. We have these hydrostatically burned elements. So we have helium, carbon, neon, oxygen, silicon. All this stuff here is hydrostatically burned. You can see how long it takes to make these things. So hydrogen burning takes a pretty long time for this star. I'm sorry, I don't remember the mass of the star. It's probably about 20, 30 solar masses. And the helium burning takes 500,000 years. And then carbon burning only 600 years. And then neon burning just 1 year, and then when you get down to silicon burning, it just takes a day to make it. But then in just a few seconds, when the star actually undergoes core collapse, you make all of these explosively burned elements almost instantaneously. But when that explosion happens, it pushes all this hydrostatically burned stuff out. So these core collapse supernovae are really two nucleosynthetic sources in one. You have hydrostatic burning out here, and you have the explosive burning out here. And that explosion pushes all this stuff into outer space. And so these core collapse supernovae come from stars of about 10 to 50 solar masses. More than that, you can get these crazy things like pair instability supernova, which I don't know much about. Now, these type 2 supernova, if I just integrated basically a Krupa IMF here and figure out how much of these stars are actually in the universe, it's really not that many stars. Only 0.8% of all stars formed are going to blow up as type 2 supernova. So it doesn't sound like very much, but if you do the integral of the IMF, then you actually find it's 17% of the stars by mass. All the stars in a Krupa IMF, if you integrate the IMF, then 17% of the stars by mass are going to blow up as type 2 supernova. That's how you get a significant amount of elements coming out of these supernovae. It's not because there's a lot of them, it's because they're massive. So to figure out what these stars are making, you go to people who are smarter than me, like Woosley and Weaver in 1995. And what they do is they make models of these stars. So they trace the star through its hydrostatic evolution, and they actually blow it up. And when they blow it up, they figure out what's made explosively, and they figure out how that explosion propagates through the star. And they even calculate how much of that stuff falls back onto a remnant. And so how much of this stuff actually gets out of the star and how much of this stuff collapses back onto a remnant, never gets out of the star. So here's the pre-explosion nucleosynthesis. Remember, we have those hydrostatically burned elements. We even have some S process that's burned pre-explosion. So we can get to the neutron capture elements even before the star ever blows up. So there's a significant number of neutrons flying around in the helium burning shells of these supernovae. And they can actually find iron peak seed nuclei and make heavier and heavier elements through the S process. So we'll talk a little bit about the S process at the end of this lecture. But you can actually get to elements well beyond the iron peak even before the star ever blows up. In the explosion, you get tons and tons of neutrinos, and you can actually synthesize new elements with neutrinos. And fluorine is one of these elements that's synthesized through neutrino capture. So you can actually capture neutrinos because, remember, these things blow up with 10 to the 51 erg, but something like 90% of that energy is in neutrinos or something like that. And so when you have all of these neutrinos streaming out, some of them are actually going to capture onto nuclei, and you can make stuff like fluorine. In explosive burning, you make some of the iron peak, so some sub-iron peak like silicon to scandium, but you also make some of that in hydrostatic burning. And then titanium to zinc is pretty much all made in explosive burning. It's possible you also get some R process coming out of the explosion too. So you can get some of the beyond iron peak elements coming out of the pre-explosion and some coming out through the explosion. But here you get the S process nuclides, and here you get the R process nuclides. These models that Woosley and Weaver and other people like Timms and Nomoto and nucleosynthesis theorists like that make are, you always see these plots in their papers. What they show is the star just prior to explosion and the interior mass. So this particular star, I believe, was 15 solar masses. And this is just the interior 5 solar masses of the star. And you can see what fraction of each layer of the star is comprised of which element. And so when they blow this up, they can say what is the energy of the shock waves that's propagating through this star and see how much of this stuff is going to get out of the star. They can even guess how much of this stuff here is going to collapse back onto a remnant. So it's more likely that this oxygen-16 is going to get out of the star than this silicon-28. So if the explosion is not particularly high energy, then this stuff can actually collapse back onto a remnant, and you can actually get certain types of supernova that make a lot of oxygen but almost no explosively burned stuff because it's going to fall back onto a remnant. It matters a lot what the mass of the star is. So the structure of a 15 solar mass star, here's the interior 5 solar masses, and the structure of a 25 solar mass star can be significantly different. And so, for example, if you look at the oxygen-16 here, it only goes up to the interior 3 solar masses. Here, it goes out to the 6.5 solar masses. So this thing is going to make a lot more oxygen. It makes sense because it's more massive, but actually the ratios, the details of the ratios of what gets out of this star is going to be different between the 25 solar mass model and the 15 solar mass model. You can't just scale up the yields of a 15 solar mass star to get to a 25 solar mass star. The stuff that gets out of the star is actually going to be different. And so when you look at these nucleosynthesis papers, it's going to tabulate the yields of these supernovae based on what the mass of the star is and also what the initial metallicity of the star is. And all of these things, all these initial conditions matter in terms of what gets created in these supernovae. So when you're making your chemical evolution model, if you want to be really sophisticated, you can go to papers like this and say, well, what is the metallicity of the galaxy at the time the star was formed? And that's going to inform what the detailed of these type 2 supernova nucleosynthesis yields are going to be. Also, you can say, I know what the initial mass function of the stars in my galaxy is, so I can look up how many 15 solar mass stars there are going to be, how many 25 solar mass stars there are going to be, and then take the appropriate yield tables for the different mass of the stars that we're dealing with. So here's the mother of all cheat sheets. If you ever want to know which nuclide comes from which nucleosynthetic source, look at table 19 of Woosley and Weisberg, 1995. It's amazing. So let's say I want to know where potassium-40 comes from. Well, it comes from carbon burning and neon burning. But potassium-41 only comes from explosive oxygen burning. So you can just look up which nuclide that you're interested in and figure out where it comes from. And you can see there's a lot of different types of nucleosynthetic sources that these elements can come from. So we have the Big Bang. We have low-mass stars that can make helium-3. So remember when I talked about stellar winds from low-mass stars? The dominant source of helium-3 besides the Big Bang is actually those winds from low-mass stars. Cosmic ray spallation is important for these lighter elements, and it only affects lighter elements because what you're doing is you're taking a cosmic ray, you're striking a heavy nucleus and splintering it apart into lower mass nuclei, and that's why you have this cosmic ray spallation affecting these lighter elements. You have this neutrino process. Remember I talked about fluorine comes from this neutrino process. It comes from helium burning, and it comes from the capture of neutrinos. This X in front of an element means explosive, so that happens when the star actually explodes. That's not hydrostatic burning. If it doesn't have an X in front of it, that means hydrostatic burning. So for example, silicon-29 comes from hydrostatic neon burning and explosive neon burning. You can actually get some light elements through the S process. You can actually capture neutrons onto very low mass nuclei in the helium burning shells to get some of these things. And as you get to heavier and heavier nuclides, starting with calcium-44, you start to see 1A pop up here. So those nuclides come predominantly from type 1A supernova. And the different modifications to 1A, so we have 1A detonation, 1A nuclear statistical equilibrium, Chandrasekhar mass. So these are different models of type 1A supernova. So now this was 1995, remember, and it's almost 20 years later, and there's much more sophisticated models of type 1A supernova. So this is a classic reference. It's a little bit outdated now, of course, because it's 20 years old, but it's still extremely educational just to read this because they go through all of the different parts of the periodic table, and they tell you this particular element comes from this part of the star, and it gets out of the star in this fashion, and it can fall back onto the star in this fashion. So if you ever want to know where all the different elements come from, this is a very entertaining read. And again, the reference is Woosley and Weaver, 1995. And if you're very confused about which Woosley and Weaver you're looking up, just sort by citations. It's got like 2,000 citations or something. So remember the main ingredients of a chemical evolution model are what type of star is producing what elements, how much of those elements, and how long it takes to get out of the star. So that how long it takes to get out of the star is called the delay time distribution. So once the star is formed, how long does it take before the oxygen comes out of that type 2 supernova, for example? Well, for these high mass stars, these type 2 core collapse supernova, the delay time distribution is very short. And what I'm doing here is I'm plotting how long it takes for the star to blow up from the time that it's formed based on the initial mass of the star. Now, when the star blows up, it doesn't blow up with its initial mass. Especially for these high mass stars, they lose a significant fraction of their mass as they evolve. So by the time a 40 solar mass star blows up, it's possible it's only 25 solar masses, because it can have a lot of mass loss before it ever blows up. But the variable that I'm plotting here is the initial mass of the star. And so what I'm plotting is sort of empirically measured from globular clusters and other sorts of things in the galaxy, the lifetime of these different stars, and I've just drawn a function that happens to fit the lifetimes of these stars. So I found 3 points, and I drew a function with more than, I drew an over-constrained function to show what the lifetime of the star is. It's actually not over-constrained because later on I'm going to show you what the lower mass range looks like, and you're going to see the same function describes the lower mass stars. So this is just a function that I fit. Don't take this as accepted wisdom or anything. But for different metallicities, this is what the lifetimes of stars are, roughly speaking. Now, if you remember from your stars class that you took when you were a first-year graduate student, or maybe even as an undergraduate, you probably learned that the lifetime of a star is proportional to the mass of the star divided by the luminosity, which basically scales as the mass of the star to the -3 power. Now, that's a very terrible description of the lifetimes of these high-mass stars, because this formula is just for, well, there's a couple of reasons, but one of them is that this formula is just for the main sequence phase of the star, so the hydrogen-burning phase of the star, which is the majority of the star's lifetime. But you can see that this function basically goes to 0 lifetime as you go to high mass, but real stars don't live for 0 lifetime. The minimum lifetime of a star is basically about 4 million years. And so this is a more accurate equation to describe the lifetime of these high-mass stars in this equation. Now, even for the very lowest mass type 2 supernova, we have delay times of about 25 million years. That's very short. So it's actually not a bad assumption to assume what's called instantaneous recycling in your chemical evolution model, which is basically as soon as the star is formed, blow it up. So we don't care that it lives for 25 million years because, yes, please.
Oh, sorry. Is that 4 million year minimum lifetime a consequence of just hitting the Eddington luminosity?
Yes, I believe it is. Don't take my word on that. I think you're right, though. Right, so when you do your chemical evolution model, there's certain types of nucleosynthetic sources, especially type 1a supernova, where you can't assume that the star blows up as soon as it's formed. However, for these type 2 supernova, because they live such a short amount of time, as soon as they're formed, just blow them up. So what that means is that oxygen is a very good element to assume the instantaneous recycling approximation for. As soon as the star is formed, it makes the oxygen. Iron is a very bad element to assume the instantaneous recycling approximation for because it doesn't come predominantly from these type 2 supernova. It comes from the type 1a supernova, which have a very long delay time distribution. Okay, now let's move on to those type 1a supernova. Remember, they come from low mass stars. And when they blow up, they tend to make explosively burned elements because they never get massive enough to make all of these elements hydrostatically. So this is one of the earlier, but also very classic citations for type 1a nucleosynthesis yields, Iwamoto et al. 1999. And you can see that the stuff that comes out of these type 1a supernova is predominantly the iron peak, as promised. So it's nuclear statistical equilibrium. Everything's going to the elements with the lowest binding energy per nucleon. That stuff up here. And so this stuff down here, not favored at all compared to this stuff up here. So these type 1a supernova make the iron peak. That's the takeaway message. Now the identity of type 1a supernova is much more in debate than the identity of type 2 supernova. Type 2 supernova, it's pretty clear that they come from high mass stars. We're even pretty certain how they blow up, which I couldn't say when I was a graduate student. But the type 1a supernova come from either single degenerate stars or double degenerate stars. So a single degenerate would be, for example, a white dwarf accreting mass from a red giant until it sort of exceeds the Chandrasekhar mass and then blows up. A double degenerate is 2 sub-Chandrasekhar mass white dwarfs orbiting each other until they radiate gravitational waves enough to explode when they merge together. Now, the delay time distributions for these two types of type 1a supernova, single degenerate or double degenerate, are very different. So in principle, if we can measure the delay time distributions for these supernova very accurately, we could identify the dominant source of type 1a supernova. I'm going to show you some measured delay time distributions in the next graph, but suffice it to say the jury is still out on this. I tend to favor the double degenerate model, but there's still a lot of slop in the observations of the delay time distribution and therefore a slop in the interpretations of what it means for the identity of type 1a supernova. So here is one observation of the type 1a delay time distribution. It's my favorite. So this is Dan Maus. He's basically made a career measuring delay time distributions for type 1a supernova. And so the way this is done is to calculate the star formation history of a galaxy and then figure out in the last X number of gigayears, has there been a type 1a supernova? Or sorry, in the last X number of years, not gigayears, has there been a type 1a supernova in this galaxy? And then figure out from that what the delay time distribution is. So if we can go to, for example, a galaxy that had a type 1a supernova, and we know that because we could see it blow up, what is its star formation history? And then go to another galaxy that did not have a type 1a supernova and has a different star formation history. We can back out what the delay time distribution for these type 1a supernova is. And this only works if you have many, many, many galaxies. And so this is basically what it looks like. It's roughly a power law. I'm not quite sure why he drew the normalization so far below what it should actually look like, but it's basically a power law with a slope of -1. And that's kind of what you expect for the double degenerate model, because when you're talking about radiating gravitational waves until you eventually merge something that started off as a binary, those things merge with a power law slope. Those things merge with a delay time distribution that's a power law with a slope of about -1. And that's different from the single degenerate delay time distribution. So I think that this graph is fairly convincing evidence that at least one dominant channel for type 1a supernova is the double degenerate model. However, when we talk about adding this delay time distribution into a chemical evolution model, things start to get a little bit hairy. Because if you look down here, look at this error bar here. So what Dan has done here is just drawn error bars that are the size of the bins that he's using. But notice that this bin spans a very large range, and there's not a lot of statistical power as you go down to lower and lower delay time distributions. And this is going to be a really big uncertainty in chemical evolution models. You see there's some hint that the delay time distribution is turning over like this. Maybe there's type 1a supernova less than 0.1 gigayears, maybe there's not. But you can see this last bin here is at 220 or so million years. So let's see what the uncertainty is between assuming that the very first type 1a supernova blows up at 100 million years versus 300 million years. So the delay time distribution that Dan has found is about 10 to the -3 times the delay time to the -1.1. And the units are the number of supernova per gigayear per solar mass. And so let's figure out what those units mean. If I form 1,000,000 solar masses of stars, then what's going to happen is I get 1,000,000 10 to the 6 times 10 to the -3. In a gigayear, I'm going to get 10,000 supernova. I'm going to get 1,000 supernova, and they're going to be distributed according to this power law, tau to the -1.1. That's for a delay time greater than 0.11 gigayears. For a delay time less than that, we don't really know what the delay time distribution is. So let's factor in that uncertainty now into the number of supernova that we get. So I'm just going to integrate this from 0.11 gigayears to 13.6 gigayears. And if I do that, then I get 4.8 times 10 to the -3 supernova per solar mass of stars formed. So if I form 1,000,000 solar masses of stars, then I'm going to get 4,800 supernova in the entire lifetime of the universe. Now let's start playing with how many supernova we're going to get out of it if we extend to infinity. Well, we get a significant number more supernovas, so you might expect that. So you can sort of figure out the entire number of supernova the galaxy is ever going to have. And notice how lucky it is that this power is -1.1 and not less than -1. If it was less than -1, then this integral will be divergent, and we get an infinite number of supernova. So it's very happy that when Dan empirically measured the delay time distribution of type 1a supernova, he got a power law that was less than -1. Didn't have to be that way. It did have to be that way, but I mean, with the uncertainty in the power law slope, it's lucky that he found -1.1, not -0.9. Okay. So now let's assume that supernova actually can start at 0.01 gigayears. It's entirely possible within the uncertainties of that observation that supernovas start at 10 million years rather than 110 million years. And if we assume that, then instead of getting 4,800 supernova over a million years, in 1,000,000 solar masses, we would get 8,100 supernova in 1,000,000 solar masses. So that's nearly twice as much iron that you'd get out of these type 1a supernova just by changing the delay time to something that's well within the uncertainties of the observation of the delay time distribution. So one of the dominant uncertainties in chemical evolution models is what exactly is the delay time, especially what is the minimum delay time for these type 1a supernovas? What is the delay time which they start blowing up? And so I've done that in one of my own papers. I've played with the minimum delay time of these type 1a supernova to see what the effect is on the chemical evolution model. So what I was doing is I was measuring the metallicity distribution of the Sculptor dwarf galaxy. And you're actually going to make a model that looks just like this in the workshop. And what I was doing was playing with all the knobs of my chemical evolution model until I could simultaneously match the metallicity distribution of the Sculptor dwarf galaxy and also the trend of the magnesium to iron ratio with metallicity, and also these other element ratios as well. So this element ratio, magnesium to iron, now magnesium is one of those type 2 nucleosynthetic products. It comes from hydrostatic burning of a core collapse supernova. So it has a very short delay time. And the iron comes predominantly from the type 1a supernova, so it has a very long delay time. So what happens is at early times in the galaxy, we don't have any type 1a supernova yet, because the minimum delay time for those type 1a supernova is 0.3 gigayears in this model. At the time I made this model, Dan revised the minimum delay time from 0.3 to 0.11 gigayears, and we're going to see what the effect of that is. And so what I did was I played with all of the parameters of the model until I could make this red line go through all the data points, and this red line match this histogram. And you see at this point, that's when 0.3 gigayears happens, and the type 1a supernova start to blow up. So we start to get a lot of iron in the galaxy. So this magnesium to iron ratio starts to fall, because those type 1a supernova are making lots and lots of iron. They don't make any magnesium. So that type 1a supernova-induced iron depression just continues on and on for the lifetime of the galaxy, because it doesn't matter if we're not forming stars, the type 1a supernova are still going to be blowing up. So we could have a single burst of star formation, and then all of the type 2 supernova are going to blow up instantly. But then forever and ever, on and on, for the rest of time, type 1a supernova are going to continue to blow up and make more and more iron. And so that iron is going to continue to depress this magnesium to iron ratio as time goes on. And so what I've done from this chemical evolution model, by matching the observations of these elements, I've backed out what the time scale for star formation is in this galaxy. Because I know what the delay time distribution for type 1a supernova is, so I can back out how long it took for this whole thing to happen. And it turns out that if I assume that the minimum delay time for type 1a supernova is 0.1 gigayears, then I get this faded line, which you cannot see at all. But this faded line that you cannot see at all goes like this. So this is the mass of the galaxy as a function of time. The gas mass of the galaxy reaches a peak, it then falls again. This is the stellar mass of the galaxy. But you can see all of the star formation is done by 1 gigayear. But now if I change the minimum delay time from 0.1 to 0.3 gigayears, everything gets stretched out by a factor of 3. So the entire deduction of how long it takes for the galaxy to form stars, when the only thing that you have is this diagram to deal with, depends very critically on what that minimum delay time for a type 1a supernova is. And so unfortunately, that's a major uncertainty, and I'm really glad that people like Dan Mouse exist to measure what this delay time distribution for these type 1a supernova is, because it really very critically affects the time scale for star formation in these galaxies when you're basing that time scale for star formation off of diagrams like this. So remember I talked about the identity of type 1a supernova. Are they single degenerates? Are they double degenerates? And there's many different models for what the delay time distribution of single degenerates versus double degenerates looks like. So these double degenerate models all sort of look like power laws with a slope of -1. And that's just a generic feature of binary stars that are going to merge by radiating gravitational waves. Whereas the single degenerate models, those sort of more look like the lifetime of a low-mass star, because you have a binary star system that's not going to be merging. It's just going to have to reach a critical point where one of the stars in the binary is a white dwarf and the other star is a red giant. So there's not a lot of time in this binary system's lifetime where that's actually going to be the case. Red giants don't live that long. They only live for maybe 40 million years. So they just have to wait for the point where one of the stars is a white dwarf and one of the stars is a red giant. And that's going to happen with a delay time distribution that sort of looks like this, and it's going to end after a certain amount of time. And you can see that's highly inconsistent with the observed delay time distribution for these type 1a supernova. I should point out, though, that there are some modifications to these single degenerate models that sort of look more like the observed distribution. So for example, this dot dash line here sort of looks like the models and then sort of tails off and stops to look like the observations there. But I think all in all, the double degenerate models do a better job of reproducing Dan Mouse's observed delay time distribution for these type 1a supernova. OK, so are there any questions about supernova before I talk about AGB stars? Good, OK, AGB stars. So if you don't remember what an AGB star is, that's OK. I still get confused about what's happening on the asymptotic giant branch. And so what happens is when we have a main sequence star run out of hydrogen in its core, then it's going to start ascending the red giant branch where it burns burns hydrogen in a shell. It's no longer hydrogen core burning, it's hydrogen shell burning. Until finally it reaches the top of the red giant branch where it has a helium core flash, and then it falls onto the horizontal branch. On the horizontal branch, this is sort of the main sequence for helium core burning. And then when it runs out of helium in the core, it's going to ascend the asymptotic giant branch again. So the second ascent up this sort of Hayashi track, where it's going to be burning helium in a shell again, rather than in a core. So we have this sort of repeating process over and over again, where we have running out of hydrogen in the core, hydrogen shell burning. Then we have helium core burning, running out of helium in the core, and then helium shell burning. So the asymptotic giant branch is the part of the star where it's going to be helium shell burning after it's run out of helium in the core. AGB stars are these really, really, really big things. They're really, 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 really puffy, and this is what one particular AGB star looks like in mass. So this is the axis here is the fractional mass of the star. So you can see about half the mass of the star is locked up in a carbon and oxygen core. Then you have a helium burning shell, and then you have this gigantic convective shell right here, which is about half the mass of the star. If I plot it versus radius now, this is the fractional radius of the star. You can see that basically the entire star is taken up by this convective zone. And like half the mass of the star is contained in that 1 pixel on the screen right there. That's the carbon and oxygen core. But you can see it's kind of a tenuous structure here. You have this gigantic convective shell. It's not very dense compared to this part of the star. The surface gravity up here has about a log g of 0, so that's about 1 centimeter per second squared. This stuff isn't really going to be hanging on to the star all that tightly. So it doesn't really have a lot of reason to stick around the surface of the star. It can very well be pushed off the star, especially when you consider that these AGB star goes through these instabilities called thermal pulses. And so on a very short time scale, look at this axis here. This is the lifetime of the star. And so when you get to 6.23 times 10 to the 7 years, when you get to 62.3 million years in this particular model of this AGB star, it starts to undergo these pulsations. And between 6.23 times 10 to the 7, 6.24 times 10 to the 7, you can see there's like a couple dozen of these thermal pulses. So in a very rapid time scale, this thing is going pulse, 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 pulse. And every time it has one of those pulses, it's throwing off a bunch of material. This is why AGB stars are significant contributors to nucleosynthesis, because they're making some stuff, they're dredging it up in these thermal pulses, and then throwing it off into outer space. So in these thermal pulses, it's just throwing off material that's been processed through nucleosynthetic processes. So I'm going to go back one slide really briefly. Yeah, please.
So is this the planetary nebula, or is that something different?
Eventually, this star is going to be a planetary nebula. So the planetary nebula is the end result of an AGB star that's done with its thermal pulses. It's thrown off a bunch of this material and it's got a white dwarf in the center. So basically, the end result of the asymptotic giant branch, it sends the asymptotic giant branch, and when it hits its last thermal pulse, it's basically just going to be a naked white dwarf, and then it ends up somewhere right here. And it's got this shell of stuff that's thrown off of it. So it's going to be a very highly red and white dwarf for a while it's got all this dusty stuff surrounding it. The stuff that's being thrown off of this thing is basically just carbon dust. It's a lot of carbon-rich material. I mean, it's a lot of hydrogen, but it's also a great deal of carbon, nitrogen, oxygen, fluorine, neon, sodium, and S-process material. Oh, and I should point out that the mass loss from these stars is up to 70%. So they can lose 70% of its initial mass during these thermal pulses. So these thermal pulses are pretty violent. It's just terrible things to these AGB stars. So this is what AGB nucleosynthesis looks like, and the reference that I like is Amanda Caracas, 2010, who revised some AGB models. And if you ever want to look up the yields of these AGB stars, you can go to her paper. And the yields of these stars vary quite a lot with mass. They vary more with the initial mass of the star than type 2 supernova models. So it's very important to know which mass of AGB star you're looking at. And so just to keep things simple for the workshop, we're not going to be putting AGB models into our chemical evolution code. We're only going to be dealing with the elements magnesium and iron. And for those two elements, we don't need to deal with AGB stars because they're not significant contributors to magnesium or iron. And that's a good thing, because if we were to be dealing with elements that AGB stars spit out a lot of, like the S process or like carbon, then we have to know very accurately what the initial mass of those stars were, which means we're going to have to integrate the initial mass function, which we just don't have time to do this afternoon. Because you can see that an AGB star of 3 solar masses makes a whole lot of carbon, but an AGB star of 5 solar masses doesn't really spit out that much carbon. And so it just depends on what the initial mass of the star is, depending on what did it create. So we have here carbon 12, nitrogen 14, oxygen 17, fluorine 19. These are the major elements that AGB stars create. Yes? There is some metallicity dependence. That is absolutely correct. I was going to say that's the difference between this red and black line. That is not true. The difference between the red and black line is old and updated. but there is some metallicity dependence, yeah. And there's especially metallicity dependence for the production of S-process elements. And the reason that there's metallicity dependence for S-process elements is because we have these iron peak seed nuclei and we're capturing neutrons onto them. And if we don't have iron peak seed nuclei to begin with, then we can't be capturing neutrons onto them. So the AGB delay time distribution also just looks like the lifetime of an intermediate mass star. Again, here's those same equations that I drew up before. They just fit those points. It's a very, very over-constrained thing, but whatever, it works. Just an empirical solution I found to all of these points to draw through the lifetime of these stars. Here, the tau to m to the -3 is a better approximation for the lifetimes of these stars. This is an even better solution to the lifetimes of these stars. So in your galactic chemical evolution code, if you're going to make one more sophisticated than the one we're going to make this afternoon, what you could do is look up through this equation the lifetimes of these stars and then say, okay, after a certain delay time of, let's say, 7.5, or let's say 8, what is that, 10 to the 8 years, then I'm going to have to be considering the nucleosynthetic yields of AGB stars of 6 solar masses. And when I have a delay time of 10 to the 8.5 years, then I'm going to have to be considering the yields of AGB stars of 4 solar masses. Okay. Now let's talk about neutron capture processes, which you're going to hear about from Carla. This is a very useful chart. It's the chart of the nuclides. Have you seen this chart yet last week? I would imagine so. Okay, you can play a drinking game with this chart too, just like you could with the periodic table. This is a very useful website, which you probably already know about. I find the chart of the nuclides just extraordinarily unwieldy. I kind of want to just print one out like this big on my office wall just so I could read it. Because you can see that, it's gigantic. But that's why we have computers, and this particular website, you can go point at the different areas of the chart of the nuclides, and you can zoom in and play with, what the half-lives of all these nuclides are. So the S process, you already know this, but I'm going to go through it just briefly anyway. The way it works is you can add one neutron on at a time. And so when you add one neutron on, you're not changing the number of protons. So the identity of the element doesn't change, but the isotope does change. So we still have iron here when we add a neutron on. Take iron 56, you add a neutron, you get iron 57. You add another neutron, you get iron 58. You add another neutron, you get iron 59. That is unstable to beta decay. And so when it beta decays into cobalt 59. The beta decay does not affect the number of nucleons in the nucleus. It just changes one of those neutrons into a proton. And so you can actually change the identity of the element that way. The key with the S process is that the neutron capture happens slower than the beta decay. And so you cannot capture another neutron onto iron 59 before it's going to beta decay into cobalt 59. So if the element can beta decay, it will. That's the principle of the S process. S stands for slow. It means the neutrons are being captured very slowly onto the nuclei. The dominant sources of neutrons in AGB stars are this reaction. Carbon-13 captures an alpha and turns into oxygen-16. Then you have an extra neutron lying around. A secondary source of neutrons is this neon-22. Neon-22 captures an alpha, turns into magnesium-25, but then you have an extra neutron lying around. So that extra neutron's got to find something. It finds one of these iron-peaked seed nuclei, and you can march up the periodic table, march up the chart of the nuclides that way. The R process, on the other hand, does not happen in AGB stars. And the key to the R process is that it's rapid. That's what the R stands for. And so you can add neutrons significantly faster than the nuclides, than the isotopes can beta decay. So the S process, you can see, just adds one neutron, then beta decays, whereas the R process can go way over here on the chart of the nuclides. It can go way over here in the chart of the nuclides, and then it's going to beta decay back to the valley of stability. And so you can see that there are certain, so this is just a zoom in, a very, very big zoom in on the chart of the nuclides. You can see that there are certain isotopes that only exist by virtue of the R process. You cannot get to neodymium-150 from the S process, because when you get to neodymium-146, then you get to neodymium-147, which is going to beta decay because it's not a stable nuclide. It's going to beta decay all the way into samarium-147. So you cannot get to neodymium-148 or 150 through the S process. You can only get there through the R process, because you've got some nuclide that captured enough neutrons to come way over here, and then it's going to beta decay back into neodymium-150. There's no way to get there through the S process. So some of these nuclides are R process only, and some of them are S process only, like samarium-144. You cannot get to samarium-144 through the R process because the R process is starting over here. If you have an R process nuclide, it's going to beta decay into neodymium-144, never going to get to samarium-144. The only way you can get there is through the S process from here. Okay, now I'm going to show, this is going to be the last slide in the talk, I'm going to show a movie of the R process. So what's going to happen here is that we're going to start off, oops, I think I have to move this to, that didn't work at all. So what we're going to do here is we're going to start off with this iron peak seed nucleus. So this is some iron. So we started off with some iron here that captured a whole bunch of neutrons, and now is way over here in the valley of, way far away from the valley of stability. What we're going to do is just going to have this incredible fluence of neutrons in this R process and see what happens. And so you're going to see all the different nuclides, many of which are unstable, be populated as the neutrons flood this iron peat seed nuclei. So we have all of this flood of neutrons that brings us way up high in the valley of stability. And eventually, we're going to let that stuff beta decay back to the valley of stability. And you're going to see that there are certain parts that build up a whole lot of nuclides, and that's because they're energetically favorable. They tend to be these things that have magic number of nucleons. Have you heard about these magic numbers yet? Okay, good. So these things have magic number of nuclei. So you can see that some of them don't have magic number of nuclei. Some of them don't have magic number of nucleons. Like this is not a magic number of nucleons, but the reason it has so much abundance there is because it started off having a magic number of nucleons and then beta decayed back to the valley of stability. So you can get these peaks in the R process that are just shy of a magic number of nucleons because they started off that way and then beta decayed back to the valley of stability. Okay, so that is the entirety I have for the lecture on the sources of nucleosynthesis, and I'm just going to give you a brief walkthrough of the workshop that we're going to do later today. And so you can download this PDF from the website that I mentioned earlier. I'm just going to flash up that website again. So if you can go here, you can go to this website and you can download this PDF. That's exactly what this PDF is. So I'm just going to leave that up just for a minute so you can write it down. Okay. And sorry, I'm so sorry. You can just go to this website and it'll list all the files in the directory, and it'll be obvious which one is the PDF. Good? Okay. And so that's what this PDF is. And so what we're going to do is we're going to have a bunch of equations, and we're going to put them all together in a chemical evolution model. And you can write this in any code you want. I wrote one in IDL, so if you get stuck, you can go to that website that I just wrote up there, and you can look at my code. And it's not that long of a code. It's maybe 40 lines long. So the basic equations of galactic chemical evolution, GCE stands for galactic chemical evolution. And I'm just going to throw up the basic equations here. It looks kind of daunting, but it's really not. I mean, it's just algebra, really. And then on the second page of this PDF, you can see the exact steps that you need to go through to write this chemical evolution model. So I'm going to walk you through step by step. You know, you add pure hydrogen gas according to this equation, then you calculate the number of type 2 supernova according to this equation. So what you're going to do is you're going to set up an array of time steps. And so I suggest that you use a time step of 1 million years, and you can make the whole array 2 billion years long. So you can make it 2,000 steps long. And then in each time step, you're going to do certain things to your array of mass. So you're going to have a mass array of hydrogen, a mass array of magnesium, and a mass array of iron. And so you're going to add pure hydrogen gas according to this equation. So you're not going to affect the magnesium or the iron arrays in this first step. It's just going to be the hydrogen array that you affect in this first step. And then in number 2, you calculate the number of type 2 supernova, calculate the number of type 1a supernova, and you can add their yields to hydrogen, magnesium, and iron arrays. And in number 3, you add it to the magnesium and iron arrays. And the table of yields is right here. So you can see a type 2 supernova spits out, actually it does spit out some hydrogen, actually a lot of hydrogen. It spits out some magnesium and some iron, whereas the type 1a supernova does spit out just a tiny, tiny fraction of magnesium, but a whole lot of iron. So you can see the ratio of iron in a type 1a to type 2 supernova is quite high, whereas the ratio of magnesium from a type 2 to 1a is high. Okay, so we'll deal with this later today, and I will pause here. I'll break here for questions. Any questions? Good, all right. Is Carla here? Oh, good. Hi. Yeah, sure.
Yeah, okay. All right. So if you have the double degenerate, if you have a mix of double degenerate and single degenerate,
Sure.
something like 60-40 or either way, is that going to produce a discernible signal? If it's not like 100% one way or 100% the other way, but if there's some half and half mix, is that going to be? Are we going to be able to pick that out?
I don't think we can with the current level of precision in the delay time distribution measurement. There's certainly a lot of room to put in a lot of single degenerate channel in there. But yeah, if there's 2 different channels, people often call this prompt and delayed 1A, then yeah, there's certainly room for that.
When you were doing your integrations on the double degenerate like delay time, you're integrating down from like 110 million years.
Mm-hmm.
So do you have to take into account like the formation of the galaxy before you do this? Like that seems really towards the low end. Like how.
So that delay time is after stars form. So once you have a burst of star formation, that's when you start the clock ticking. So it's the delay time not from the beginning of time, but from when stars form. Does that make sense?
Well, then why do you go up to 13.6 billion?
Oh, good question. Yeah, so that would be assuming that there was a burst of star formation at the beginning of the universe.
Okay.
That's right. I just picked that number as an upper limit.
For a computational reason,
Right. Yeah.
could have sinned worse, I'm sure. So.
Right. I could have chosen 10 billion years. It was just an arbitrary number.